In the lesson about wind, we talked a little bit about air pressure, and in order to understand why weather does what it does and why weather moves around and why storms move around and storms develop, we have to understand air pressure a little bit more. So we're going to go into that a little bit more in depth. So air pressure affects wind. Excuse me, it's one of those things that's going to affect the movement of air around the planet, because basically that's what wind is. It's just difference in air pressure, and as air moves from an area of one air pressure to an area of another amount of air pressure. And that happens because of the sun. So the sun heats up the earth unequally. We know that warm things rise, and we talked about conduction, convection, and radiation, right? So the radiative energy comes from the sun. It warms up the surface of the planet. The surface of the planet is touching the air that's right above it through conduction, right? And then the air rises through convection. So when the sun doesn't heat up the planet the same way, we end up with air rising in some places and sinking in others, which gives us differences in air pressure, which means the air is going to move around, and that gives us wind. So the differences in air pressure is one thing that's going to control wind. The Coriolis effect, which I'll explain in just a minute, and then also friction. So we talked a little bit about air pressure, and that's just the weight of the air being forced down to the surface. And it's coming down to the surface because of gravity. So gravity, because we have a gravitational pull, it's what keeps our atmosphere around us. It tries to pull it in towards the center. The spinning effect of the planet tries to kind of push it away from the surface of the planet. If you've ever gone to a fair or carnival or something like that, and you've been on the ride where you stand there and it's a big spinny thing, and then you like stick to the walls, that's called centrifugal force. It's the force that pushes outward from. So it's the balance between those two forces, the force of gravity pulling in and the centrifugal force of the planet spinning. Where that balances out is where our air pressure is at. And air pressure is greater closer to the surface of the planet because you're closer to the center of gravity. So there's air pressure going in all different directions, and we use a barometer to measure air pressure. So there's different kinds of barometers. Here's one of them. This is a Mercury Barometer. And so what happens is that this plate down here is flexible, and the pressure of the air pushes that plate down and squeezes the compartment that has mercury in it. And the mercury is forced up the tube. It has markings like a thermometer on it. And so we call them millibars, is how it's measured, is in millibars of mercury. And so we say either the mercury is rising because there's greater air pressure because it's getting squeezed more down here, which forces more up here. Or we say that the mercury is falling because there's less air pressure, and so we have less squeezing going on. If the mercury is falling, then that means there's an area of low pressure coming in because it's low pressure, right? There's not as much pushing down. If we have an area of high pressure that's coming in, then that's going to squeeze down on that more, and it's going to push the mercury back up. And we'll talk about weather conditions that are associated with areas of low and high pressure in a few minutes. There are also some that are that have a dial on them, so they look like a clock face kind of, and the back of the back of the clock, or the back of the barometer, is a flexible metal. And the same premise holds, is that as the air pressure increases, it pushes on the back of that metal and it causes the dial to spin, and it shows, and so it reads the amount of air pressure. So it works kind of like a clock, but it's a clock that happens because there's pushing on the back of it by air pressure. So our differences in our pressure, we can show that on a map. And the map that we use is called an isobar map. So if you're familiar with, you go hiking or anything like that, and you're familiar with a topographic map, a topo map shows, it has circles on it and lines on it that show areas of elevation. So you know if the lines are really close together, that means you're changing elevation really fast, and that means it's steep and you're going up a steep hill. The same thing holds true with isobars. Isobars are showing us the amount of mercury, okay, the millibars of mercury, the air pressure that's in an area. And so the closer those lines are together, then that means that it's really windy because the air pressure is changing really quickly. The further they are apart means it's not changing as quickly, which means it's going to be more calm and still. So the pressure gradient is just the difference from one line to the next. And so how far those are away from one another will tell us if it's going to be windy or not, or if it is windy in an area. So here's an example of an isobar map. It looks a lot like a topographic map. It's just over a larger area. So you can see that around the area of low pressure, it's a little bit windier. Our lines here are a little bit closer together, and so we're going to have faster wind speeds. These are called weather stations, these little symbols right here. The center is over the station itself, so that's like the city where the weather station is. This is called the staff, the line that's coming off of there, and that tells us which direction the wind is coming from. So in this instance, the wind is coming from the northwest and going towards the southeast. And then these flags on here tell us how windy it is. So you can see over here on the side what the key is. And so in this weather station right here, you'll see that it has one filled in triangle and one half mark. So right here, so that means it's 61 to 66 miles per hour winds in this particular area. So it's pretty windy here. If we go over here towards the area of high pressure, where you have our weather station, so we're over in Canada now, we can see that we only have one full line up here, which means that it's 9 to 14 miles per hour, which is not very windy at all. We get out here, we're away from both of them, and now we're almost calm. We're at 1 to 2 miles an hour, and here in Arizona, we have calm conditions, so no wind at all. So we can tell a little bit about what the weather is like in particular areas of the country by looking at a map like this. So one of the things that's going to impact our wind is air pressure and the changes in air pressure. Another thing that's going to impact our wind is the Coriolis effect. So the Coriolis effect is the deflection of wind based on the spin of the planet. So when we talk about our planet spins, and we have some things that are really kind of firmly attached to our planet, like our continents. Yes, they sit on that molten mantle, but they're really big and heavy, and they're not going to move around just because the planet is spinning. That's not what causes the movement, okay, of our continents. We know that it's because of the convection currents, right, that are in the mantle. Water, though, and wind are not as firmly attached to our planet. They move much more easily, and so as the planet spins, the water and the wind do not spin at the same speed as the rest of the planet because they move differently because they're not actually attached to the planet. And so because of that, they don't keep pace with the planet. And so they get bent and they get deflected to the side. And there's a little video clip that you can watch after this that actually shows some deflection based on the spin of the planet. So in our northern hemisphere, the wind and our oceans and water and stuff like that get deflected to the right, and in the southern hemisphere they get deflected to the left. And so it causes movement of the air away from the equator, basically. A little while back we had a little lesson on winds, and we talked about the global wind belts, and this is what helps to cause the global wind belts, is this deflection of air based on the spin of the planet. So here's our planet. Okay, the planet is spinning this way, but the air is not firmly attached. And once you leave the surface of the planet, then you're no longer spinning with the planet. And so for some people, like pilots, this is a big deal, because if I take off in somewhere, up in northern Canada or something like that, and I want to go down to Mexico, if I don't take into account that when I'm up in the air, the Earth is going to spin underneath me, then I'm not going to end up where I want it to be. So in here, they have their target. I'm not sure why they have their target being in the middle of the ocean, but they do. So if I wanted to get here, but I didn't take into account the fact that the Earth is going to spin underneath me, okay, then I wouldn't end up there. I would end up somewhere else in the ocean, okay? But if we were looking at it like on a continent or something, we start out here up near Canada, we want to go down here into Central America, okay? In order to get there, we actually have to aim for over here. So as the Earth spins underneath, you kind of meet in the middle. It's less of an impact if you're going this way along a line of latitude, okay? Because then the Earth, when it spins, you're still staying right over the same area of latitude. It only impacts you when you're going north to south. Now, the question always comes up, so if I jump in the air, does the Earth spin underneath me? So our Earth takes 24 hours, right, to spin once around on its axis. So hypothetically, if you could jump and stay in the air for like an hour, then the Earth, you would not land on the same spot that you jumped from. Now, of course, we can't really stay in the air for an hour. If you're attached to something that's attached to the ground, then you're still moving with the planet. So you'd have to actually, like, if you were in a hot air balloon, though, up in the air, and you stayed, and you tried to stay, like, in the same place for an hour, the Earth would actually move underneath you. So you would be able to see that. So we have our factors that affect our wind. Remember, we have our differences in air pressure, we have the Coriolis effect, and then we have friction. So I want you to imagine you're in a car, and you're driving along, and you're going at a normal speed, but a dog runs out in the middle of the road, and you've got to slam on your brakes. And so you slam on your brakes, and the car, you can feel it if you're driving, you can feel it that the car tries to go off to the side while you're braking, because you're braking really fast. And it does that, it scoots off to the side like that because of friction. The friction of the tires on the ground as you're braking really hard causes you to veer off to the side. So friction actually slows the air down, kind of like your brakes were slowing you down, and it causes it to change direction. So when we look at what, excuse me, all our different influences, the things that can happen, we have all of these things acting at once. So we can't say that it's just friction that slowed down the wind or changed the wind direction. It's really the combination of all these things. So when we talk about, we've got the air pressure, we've got the friction, we've got the Coriolis effect, and as a result, this is the way that the wind blows. So you can't take them in isolation. You can't just look at one factor at a time. It's really a combination of all those areas. Okay, on your handout, you have an area for your air masses where you have the name of the air mass, the abbreviation for the air mass, you have a description of what it's like with that air mass, and then where it came from. And you want to make sure that you get all those things filled out as you're going through these notes. If you miss something, you'll want to go back to the video, because this is a pretty important concept, because this tells us what kind of weather we could get as air changes direction. So we said this a little bit before, that the front, right, is the boundary between two big chunks of air that have kind of a common characteristic of air temperature and humidity. And those big chunks of air are called air masses. So we've got warm air masses, we've got ones that are warm and dry, we've got ones that are warm and moist, we've got cold and dry and cold and moist. And where they come from is going to determine what that characteristic of that air mass is going to be. And then as they meet over continents, that's going to tell us what our weather will be like. So they're going to move, most of our air masses are going to move with the direction of the global winds and the jet stream. So this is just an example of a cold, dry air mass that's getting caught by the airstream. And if it were to be able to go all the way down the North American continent, it would drop temperatures as it goes through. And we see this all the time in the wintertime. We could have a time where it's up to 70 degrees, and then the next day it's in the 50s. And that's because this cold air mass came through, pushed out the warm air mass, and all of a sudden our temperatures changed. So, on your chart, once again, we're going to talk about these different air masses. Here's just a picture of where they all come from. So the first one we're going to talk about is continental polar. We go back here again. Continental polar comes from over the top of a continent in a polar region. So we're right here, we're at the North Pole, and we're over the top of Canada and Alaska. Okay, so our continental polar, because it's coming from a polar region, polar tells us that it will be cold. Over a continent tells us it's going to be dry, because it doesn't have the ability to pick up as much moisture. So on your chart, you're going to have a continental polar air mass, which is abbreviated as CP, and it is cold and it is dry. Continental means cold, or sorry, continental means dry, and polar means that it will be cold. So these big air masses, so a few years ago, there was a time when it was warmer in Alaska than it was in Florida. And that's because this continental polar air mass dropped down from the polar regions, and the jet stream dipped so far down that there were freezing temperatures in Florida, and it was like in the 50s in Alaska because a big warm air mass was sitting over the top of Alaska. So continental polar air mass in the wintertime brings us our really cold temperatures too. And I'll show you a little bit with the jet stream. Our jet stream starts all the way up in the North Pacific, up off the coast of Alaska. And it can actually pick up as the jet stream comes over the top of Alaska and Canada before it drops down. It can pull some of this continental polar air down to us. It can also pull some of the maritime polar down, and that's where we get our big cold, wet storms in the wintertime. A maritime tropical, maritime refers to the ocean. So if it's maritime, it's moist. And if it's tropical, it means that it comes from around the equator, which means that it's going to be warm. So tropical means warm, maritime means moist. I'm going to go back to my picture again. So our maritime tropicals are going to start between 0 and 30 degrees north latitude for us, and then also south latitude for the southern hemisphere. And they're going to start from over the top of the ocean. So here we're getting closer to the equator. We sit in Arizona in Phoenix at about 35 degrees north latitude. So we're looking at ones that start down around Mexico and down to the equator are the ones that influence our weather up here. So maritime is moist, tropical is warm. So, and this is where the maritime tropical, when we get our monsoons in the summertime, this is where the moisture comes from because high pressure will sit over the top of the four corners, and the way it spins, it'll actually pull moisture up into Arizona. So that's the one that feeds. And when there's tropical hurricanes and things like that that hit Mexico, a lot of times, depending on the pressure system that's sitting over Arizona, if it's high pressure, it'll actually pull it in then, and we can get rain. Sometimes at times we don't usually expect it because of that. It also is going to be the source of precipitation on the East Coast, but it also impacts us here on the West Coast. Maritime polar. So maritime, once again, means moist. Polar means cold. So now these are cold, moist air masses. And these ones actually start, I'm going to go back to my map here, they actually start over Siberia as a CP, or a continental polar. They move over the top of the ocean, and they pick up moisture, thereby becoming maritime polar. And then they either stay up north, depends on the jet stream now, because the jet stream can either dip way down to us, like this, or it can stay up high. If it stays up high, then it's going to be the source of rainfall in the wintertime up in the northern tier states, rain, snow, everything. If it dips down low to us, okay, then that's when we get our winter rains. If it's a cold storm, it's coming from a maritime polar air mass. If it's a warm storm, sometimes we get them on what they call the Pineapple Express, and that's where it came from out over near Hawaii, and it's a maritime tropical. So here it is coming from over the top of Siberia and moving across. You'll see here what says stable and unstable. When an air mass is cold, it can't hold as much moisture, which means it's not going to rain, it's not going to be as windy and all of that, so they call it a stable air mass because there's not much happening going on in the sky. Unstable now, that because it has a lot of moisture in it, and because it's starting to warm up a little bit, now we can start to get some air rising, and when we have moist air rising, we know what happens, right? That's when we start to get clouds and storms. And so that's why they call it unstable, because things are happening in the atmosphere. Our last one is our continental tropical. So continental meaning over the continent, so it's dry. Tropical meaning that it's warm. The CT air masses start, for us, they start usually down around Mexico, coming up from Central America up through Mexico and then up through the central part of the United States. They don't have any moisture associated with them, and so the air mass just is really, really warm. This is the cause of Indian summer. If you're from the Great Lakes region, or if you're from that upper Midwest area, it's where it's just really warm later in the year, like into October when you expect it to be cooling down, and it just doesn't because you've got the CT air mass coming up.